Hello, welcome to Algebra 2B Live. We're going to be doing week 4, a video lesson over operations with rational expressions. So for week 4, make sure you go through our textbook. Not all the stuff I cover for week 4 is in this lesson, so some of that I do expect you to scan through and look through the examples of the textbook. Use this video and the textbook and the paper pencil problem video links to do all your assignments for this week, and let me know if you have questions as you're working on stuff. Here's our objectives. This is what we'll be working on for this week. If I give you a rational function with different degrees for the numerator and denominator, can you identify the asymptotes, the domain, the range, and any holes in the graph? So again, more graphing with rational functions. And then we're going to be switching over to rational expressions. If I give you a rational expression, can you simplify it using the same procedures of fractions? Find the common factors in both the numerator and denominator and divide them out. If I give you two rational expressions, can you multiply them and using the same procedures with fractions by multiplying across the numerator and denominator? And then if I give you two rational expressions, can you add or subtract them by first making sure they have common denominators? So graphing, simplifying, multiply, divide, and add or subtract. Some basic stuff, only with rational functions, it gets a little bit more complicated. All right, so we looked at rational functions and their graphs last week, looking at how do you find horizontal asymptotes, vertical asymptotes. Again, one of the big ideas is we find the horizontal asymptotes by looking at the coefficients. If both the numerator and denominator have the same degree polynomial, then we just simply look at the coefficients of the leading degree term and we divide them. We find any vertical asymptotes by looking for which x values make 0 in the denominator. The domain and range are always all real numbers except for when we have any asymptotes. Finally, a graph will have holes when you have a common factor in the numerator and denominator. We didn't go over this, but there's some good examples of this in your textbook. And then we can still find x and y intercepts by putting 0 in for x or 0 for y and solving for the other variable. So these are all things we did last week. Factoring the numerator and denominator really helps with finding these and doing these and graphing these and finding all these specific critical values of the graph. We're going to do one more just to really dig into it. So here we got this function, f of x equals x plus 4 divided by 2x squared plus 4x minus 16. We're going to go through finding asymptotes. We're going to go finding domain, range, any holes, if there are any, and talk about what this graph looks like. Okay, so first of all, before I want to do that, let's factor this thing out. The numerator is just x plus 4, but let's factor out what's in the denominator and rewrite this function out. So if I split this up, there's a common factor of 2. And so I'm going to rewrite that as 2 times x squared plus 2x minus 8. And now I need to look for two numbers that multiply to negative 8 but add to 2, and that's going to be x plus 4 times x minus 2. And then I still have this factor of 2 at the beginning. So there is our new function that we're going to be working with. And because I factored it out, it's going to be a little easier to see what's going on. Let's first start with some asymptotes. So vertical asymptotes, up and down places, up and down lines that this graph gets really close to. I want to look for when the denominator equals 0. And I see that if I make x 2, then I'm going to have a 2 minus 2. That's going to make a 0. And then also when I have an x as a negative 4, there's going to be something interesting going on. What I'm going to point out right now, though, is we have an x plus 4 factor and an x plus 4 factor, both in the numerator and denominator, that are going to divide each other out. This is what happens to give us what's called a hole in the graph. When I graph this, we're going to see that there isn't an asymptote at negative 4, but what really is happening is there's going to be a chunk of the graph that's just not there. At x equals 4, there is no value for the graph. So we have a hole, because I have x plus 4 in the numerator denominator, we have a hole at x equals negative 4. All right, so we got our vertical asymptote. We're gonna have 1 at x equals, whoops, 1 at x equals 2. X equals -4 is not going to be an asymptote. It's actually going to be a hole. Now let's look for a horizontal asymptote. What's that horizontal line that the line gets close to? Well, remember we talked about, think about when our x values get really, really big and what is the tendency of the graph. Well, as x gets very big, that's great, but on the bottom, I've got an x squared. The bottom polynomial is a degree 2, where the top polynomial is a degree 1. So what's going to happen is x squared gets bigger a lot faster than x to the first power does on the top. So if the bottom gets bigger much, much faster than the top, you're going to see the whole value of the function, when you have a small number divided by a very large number, it's going to tend to get really close to 0. So we have a horizontal asymptote of y equals 0, or just the x-axis. It's going to get closer and closer to 0 as I go to the right, and as I go to the left, there's going to be a horizontal axis at, or a horizontal asymptote at y equals 0. All right, we got asymptotes, we got holes, and now we can start to play around with domain and range. So the domain, that's all your x values, right? So we have all x values except for when x equals 2 and x equals -4. Those two values, except x not equal to 2 or -4. Those are the only two x values that are not going to work in this function. I get a divide by 0 when that happens. For the range, it's all y values except for the horizontal asymptote. So except for y equals 0. Except y can't be 0. I'm never going to get a y value of 0 in this function. So there we go. Again, taking our graph, thinking critically about the numerator, denominator, factoring, thinking about what's dividing by 0 helps us find all these values. Let's go ahead and take a look at the graph and just verify some of these things we found here. All right, here we are. So there were a couple things. Remember we said there was a vertical asymptote at x equals 2 because I have an x minus 2 in the denominator. And so you can see, yep, from this way it gets really, really close to 2. And coming from this way it gets really, really close to 2. So I'm going to go ahead and even make that. So x equals 2 is one of my vertical asymptotes. Now we thought initially x equals -4 might be one, right? But look at what's going on in my graph. There isn't one, but watch what happens when I get an x value of -4 right there. It makes a little white dot on my Desmos calculator and it says, hey, at x equals -4, this thing is undefined. That's what we call a hole. You can't even tell because to the right of it and to the left of it works just fine, but exactly at -4, it won't work because you get a 0 in the numerator and a 0 in the denominator. You can't have 0 divided by 0. So just some funky stuff going on, but when you just look at it initially, you may not even realize there's a hole. That's why you need to be able to analyze the function, factor it out, and look for common factors in the numerator and denominator. Okay, we do have a horizontal asymptote. You can see that as you go to the right, it does get close to 0 that way, and as you go to the left, it does get close to 0 that way. And there is a graph of our function. All right, let's go back, and I think we've done enough for graphs now. I think we're ready to start learning some other stuff. One little final caveat on graphs. Again, the first section in this week, 4.1, you talk about when you have a numerator and denominator with different degrees and how to find the horizontal asymptote. It's really easy if the bottom polynomial is the biggest degree because the horizontal asymptote just goes to 0. That's just the example we did. But if your numerator of your rational function has the larger degree, it gets a little bit more complicated. It has what we call a slant asymptote. So it's going to kind of go towards a slanted line. And what you do is you actually divide the polynomials. You divide the numerator and the denominator. And you take your result, whatever it is, you ignore the remainder and you just look at what you get for the division. And that's going to be the line that your rational function will tend towards. Again, I'm not going to go over this. There's a good example in your textbook. There's other things that I really want to focus on for this video lesson. I just wanted to point out a little bit about what happens when you do have different degree polynomials. Okay, completely switching gears. We're going to get into simplifying rational expressions now, and then adding, subtracting, and multiplying, dividing. But let's first start with something we know. How would we simplify this following fraction? We have 24 divided by 30. How would I go about simplifying it? Well, when simplifying, we may not necessarily kind of do a lot as a head, but what we do is we find common factors in the numerator and denominator, and then we divide them out to make a simpler fraction. We had 24 divided by 30, right? Well, I can rewrite that as 24 is 2 times 2 times 2 times 3. I've factored it out. 30 I can reduce to 2 times 3 times 5. So I've done all the factorization. And there's some common factors. 2 divided by 2 divides each other out. That's 1. 3 divided by 3, we factor out the 3. And what are we left with? 2 times 2, which gives you the 4, over 5. So I can reduce this thing down to 4/5 once I divide out all the common factors. We know how to do that. That's nothing new when we simplify fractions. We do the same exact thing, however, when we're asked to simplify rational expressions. So here we go. We've got x to the 4th plus 8x, all divided by x to the 4th plus 5x to the 3rd plus 6x squared. And I'm going to ask you, let's simplify this down. We'll do the same exact thing. We want to factor. So hopefully you guys remember how to factor all your polynomials. Up on the top, I've got a common factor of x. That gives me x times x to the 3rd plus 8. And now I recognize, I've got something to the 3rd power, and 8 is just 2 to the 3rd power. So I'm going to pull out my sum of 2 cubes, and that factors into x times, that's that same x right there, but the factor of 2 cubes is going to give me x plus 2 times x squared minus 2x plus 4. And you can look up this formula for factoring. If you have something cubed plus something cubed, just look the formula up, follow the directions all the way through. Again, we've done some of this, but there we go. We just completely factored the numerator. Now, if I want to simplify it, I want to look for common factors in the denominator. So I got to factor the denominator out. I'm looking right off. I've got a greatest common factor of x squared. So I'm going to pull that out first and see what I got left. I'm left with x squared plus 5x plus 6. And this is a little easier to see that it factors just into x squared. I need two numbers. This is a nice leading degree of 1. So I need two numbers to multiply to 6, but add to 5. It's going to be 2 times 3 and 2 plus 3. So it's going to factor into x plus 2 times x plus 3. Okay, look at what we got when we factored it. You'll notice now we're going to look for some common factors. If I have x squared, that's the same as x times x, and one of these factors of x can divide out. I'm going to divide that x with that x, and we've just simplified this thing down a little bit. We also have two factors of x plus 2. There's x plus 2 divides out with x plus 2. That makes things a little bit nicer too. So what do we have left when it's all done? Well, I still have x squared minus 2x plus 4. That's my remaining polynomial in the numerator. Divided by, I still have this factor of x here. So x times x plus 3. Notice it is a little bit simpler, right? I now only have a degree 2 polynomial in the numerator denominator. We've simplified out some of the factors, and we have a less complicated algebraic expression to work with. So that's what we're doing when we're simplifying. Just simply factor the numerator, factor the denominator, and divide out common factors and leave whatever you have left. As you do adding, subtracting, multiplying, dividing, this is always the last step that you really want to do. Is you want to, well, usually the first step is to factor, but then at the very end you want to make sure you've got the most simple rational expression that you have. All right. Do you remember how we did the following? We did adding, subtracting, multiplying, dividing with polynomials. And then we learned how to add, subtract, multiply, and divide radical expressions. And then we did adding, subtracting, multiplying, dividing functions. Now we get to start looking at how to do all four of those operations with rational expressions. The key is to just remember how to work with fractions. How do I multiply 3/4 times 2/9? Let's review that. Hopefully, you remember with fractions, when you multiply across the numerator. So 3 times 2 is going to give me 6. And you multiply them on the denominator. 4 times 9 gives you 36. And then you simplify it. So I say, okay, well, 6 is a 6, but in the bottom, 36, I can rewrite it as 6 times 6. So we factored it out, and look, 1 factor of 6 divides with 1 factor of 6 to leave 1/6. So we simplify it at the end. That's not too hard, right? But we're going to do that same exact process to multiply rational expressions together. Factor, multiply across the numerator, multiply across the denominator, divide out common factors, and we're done. Let's do one. Oh, here we go. I just summarized it. Factor the numerators and denominators first. Multiply across the numerators, multiply across the denominators, and then simplify the resulting rational expression. You can pause this video and write this down if you want to. This is the steps for multiplying. Here we go. Look at this. We're going to multiply all this together. It may look daunting, but it's not that bad if we go step by step. First thing I want to do is just factor it all out. So x squared plus 9x minus 36. I'm going to go through the factoring pretty quickly. Again, you can review factoring, look back on previous stuff. Excuse me, but it factors into x plus 12 times x minus 3. In the denominator, difference of 2 squares. So that factors into x plus 3 times x minus 3. Now all that is multiplying by, on the top, let's factor that. So we've got two numbers that multiply to 15 but add to 8. That's going to be 5 and 3. So we got x plus 3 times x plus 5. And on the bottom, that's going to factor into x plus 12. You know what? I wanted to write that. I totally butchered that example. I wanted to make this minus 12 right here. So change this to x squared plus 11x minus 12. Not going to work out if I don't do it. So it's factorable if it's x squared plus 11x minus 12. And so we get factors in x plus 12 times x minus 1. All right, hopefully you caught that little error. Again, change this addition sign, change it into x 11x minus 12, and then it'll work out from there. Okay, so we did step one. We factored everything all out. Now, we know it's all going to multiply together. Do you see any common factors already that are going to divide out? Well, we have an x plus 12. That's going to divide out with this x plus 12. We have an x plus 3. That's going to divide out with this x plus 3. And we have an x minus 3. It's going to divide out with this x minus 3. So when we're all done, what do we have left when I multiply across the numerator and denominator? I just have x plus 5 divided by x minus 1. That is my simplified resulting rational expression. Look at that. Would you have thought all that simplified into all that when I multiplied them all together? So always factor first. Here's the mistake I see students do. Usually there's always a few students that do this and they get in a world of hurt. They look at this and they think, okay, FOIL this out. So they take, let's take x squared, multiply that to get x to the fourth. And then x squared times 8x gives me plus 8x to the third. Then x squared plus 15 gives me plus 15x squared. Then I go to the 9x. 9x times x squared gives me plus 9x to the cube. And then 9x times 8x gives me plus 72x. And then 9x plus 15 gives me, 135x. Now, I'm not even going to go anymore because we still have the negative 36 to go through. But look at what you end up on the numerator. You get this gigantic bunch of stuff that you really can't do anything with, divided by another gigantic bunch of stuff that you really can't do anything with. And then they get stuck. And like, how do I simplify that? It's easier to factor right away and then to work with binomial factors and to keep it as binomial factors. All right, let's move on. Division. If I want to divide rational expressions, remember with fractions, we just change it to a multiplication problem with the reciprocal. So, even though this is 5 divided by x squared minus 25, or sorry, divided by x minus 3 over x squared plus 3x minus 1, I'm going to change it to multiplication. So it becomes 5 over, I'm going to go ahead and factor the bottom. So that's x minus 5 times x plus 5, x minus 5, times, and then this goes in the numerator, and then this goes in the denominator. So x squared plus 3x minus 10, I'm going to factor that out into x plus 5 times x minus 2. And then x minus 3, there's nothing to factor there, so that just stays in the bottom. But there you go. It's now a multiplication problem. And multiplication is pretty easy. We know how to do that, right? Just multiply across the numerator, multiply across the denominator. First, I'm looking for any factors. X plus 5 divides out with x plus 5, so I don't need that. So then it becomes 5 times x minus 2. And on the bottom, we have x minus 5 times x minus 3. And I can go ahead and leave that in my final form. There we go. We just successfully divided these two rational expressions, changed them into multiplication, factored where we could factor, divided out common factors in the numerator and denominator, and then multiplied across the top and bottom. Okay, adding. So multiplication and division, not too bad. But let's think about adding fractions. To add or subtract rational expressions, I need a common denominator just like when we add or subtract fractions. So let's look at this here. We got 5x over 2x squared plus 2x squared plus x minus 5 plus 3x plus 1 over 2x squared plus x minus 5. We already have common denominators here. So this is all set up then to say, okay, well that becomes 5x plus 3x plus 1 over 2x squared plus x minus 5. I can just add the numerators together, and then we've added them together. Now I still got to simplify. So let's see what we can do here. On the top, 5x plus 3x is going to give me 8x plus 1. And let's see if we can factor the denominator. So I play around with some things. 2x squared, that's going to be 2x times x. 5, the only way to get that is 1 times 5. Can I make that work? If there's a 5 here, I'm going to get a 2 times 5, that's 10. That's not going to work if the 5 is here and the 1 there. I'm going to get a 2 and then a 5. No. It's unfactorable. Can't make it work out. So I'm just going to leave my answer as 2x squared plus x minus 5. And there we go. We've just successfully added them together. So again, next week we'll look into what happens when you don't have common denominators, and there's some work we can do. But for now, this week, just start looking at already they have common denominators and practice combining within the numerator, either using addition or subtraction, and then see if you can simplify the result. All right, that's what we got. So what did we cover? Again, a little bit of graphing, a little bit again finding asymptotes, domain range, and holes in the graph. But then we looked at what if you have a rational expression? How do you simplify it? How do you multiply and divide? And we started looking at how do you add and subtract. So work on all that stuff and have a great rest of your day.